7-1. This one has answer key on the back, so I'm only doing the limited that was being asked. So number 4. Okay, least soluble. This one has to do with KSP. You don't have to worry about KSP for this time being, but if you're wondering about this, basically KSP is equilibrium when you're dissolving. Let's say, for example, dissolving of NaCl. Okay, we know NaCl solid. When you put in a water, you're gonna get Na plus Cl minus, and these are called aqueous solutions, so they're AQ. Right, so remember in the equilibrium, when you write K, or in this case KSP, when you write K, you do not write solid or liquid. So you do not write this, you do not write water. What you're gonna write is you're gonna write these two. So you're gonna write Na plus concentration, and you're gonna do Cl minus concentration, and that's it. So so what does that mean when things are dissolved and when things are very, very soluble? When things are soluble, your KSP number will be large because you will have a lot of these ions. When things are not so soluble, your KSP is going to be small. That's all it is. So least soluble level, we're going to looking for lowest KSP. Now when we say lowest, be careful with the power. The powers is biggest negative number, right? Negative 36, that's your biggest one so far, biggest negative number, therefore lowest value. So CUS is gonna be least soluble. Okay, let's go through. We're good with that. Let's look at 11. Okay, reaction. Okay, which one is true? Remember K value. K is products over reactant. Okay, now this K value is bigger than 1. What does that mean? That means mole product, okay, compared to reactant. So therefore, B is bigger than A. Oops, right there. See, right? Okay, let's go over 13. Consider the following equilibrium. Equilibrium cannot be established when blank is placed in this. Okay, so when can we not have equilibrium? Obviously, the easiest one is you either have a whole reactant or whole product. If you don't have them, you won't have an equilibrium. Okay, meaning the answer is gonna to be B, because B only have one of the reactant in there. Yeah, how you gonna react to make SO3, right? Okay, 16. Reaction vessels. Let's see what's happening. Okay, we're looking for Kp pressures. All right, so when a system comes to equilibrium, okay, my sister's raging over there. PHI, pH2, and PI2 is gonna be that. Okay, notice you don't need to do I's because it's an equilibrium. Add equilibrium, then these. Easy, product over reactant. Okay, 0.086, 0.086 divided by HI 0.808 squared. That's all you're doing. Now notice that they are kind of quite similar. You can kind of calculate it about approximately speaking. I will make these to be 0.8. Okay, how do I make it? Make it into 0.86 times 10 to the negative 1, right? Or 0.1. Okay, and this is also 0.86 times 10 to the negative 1. This is 0.808, 0.808. Notice what I'm trying to do. I'm trying to approximate. I'm trying to say this is about this, this is about this. About, again, not exactly supposed to be. My bottom is a little bigger, so my answer is going to be less than what these multiply, which is 10 to the negative 2. So less than 0.01, or less than 10 to the negative 2. So that means, if you look, less than that, 10 to the negative 3. Okay, almost 10 to the negative 2, but not really. That's my answer. Okay. 17. At the high temperature, okay, what's happening? We have an equation here. Mixture of this and this is combined in the, okay, notice the tricky part right there. Volume is no longer 1. You cannot just use that as a molarity. Okay. Alright, so what we're gonna do? We're gonna try to do the ice table again too, because you don't have all this stuff. So H2, Br2, HBr, 2 of them, arrows. Okay, initially how much did we have? 0.6. Okay, now notice that it's 2 liter. So when you finish, whatever you get mole, you have, oh wait. Oh, no, you don't have to. This is extra. You gotta look at your unit here. We're lucky. They're asking for mole. Or not lucky, because if you think you're molarity, then you will be wrong. So we're asking for mole. So guess what? Ignore that volume. You can ignore it if as for mole only and given mole in a question, right? Okay, so let's try doing this. What's gonna happen? H2 is 0.6, A2, Br 0.44. This is gonna to be 0, minus x, plus, careful now, 2x. So that's a change. Okay, ICE, equilibrium, 0.6x2 minus x, 0.44 minus x. This is just 2x. All right, what we're gonna do? And then they give you something. They say at equilibrium, you have 0.566 of H2. That means this is equal to 0.566. So for H. Okay, 0.566, 0.82, 0.682 minus x is equal to 0.566. Okay, so what you gotta do? You're gonna subtract that. Ooh, let's see how we're gonna subtract that. Okay, 10, 6, oh wait, yeah, 6, and then 2. So it's gonna be 6, 7, 6, 1, 1, I think, right? 6, 6, 12, 1, 6, 7, 8, and then 5, 1, 6, yeah. That's gonna be x is equal to, okay? So x is equal to that. What are they asking? They're asking for BR, so just plug it in here, okay? So BR is that. Plug that back in there. So 0.44 minus 0.116. Okay. 10, 6, that's gonna be 4. 9, 1 is 8. Wait a minute. Hold on. Yeah, 10, 6 is 4, yes. 9, 1 is 8. No, not 9, 1, 4. 1, 1. So that's gonna be 2. And then that's gonna be 3. Okay, 3, 2, 4. Yes, 6, 4, and 1, 2, 3, 4. Yeah, 4. Yep. So 3, 2, 4. Okay, math. Oh, there's a lot of math still. Okay, 22. 2 mole of this. What is the value of equilibrium constants? A, B, C, and 40% is dissociated at equilibrium. Okay, 40% dissociation. Okay, so what's happening? That means A is becoming B and C by 40% amount. Okay, we can solve for this. A, B, C. What is happening? That means if I have 100, 40% of that will be gone. So minus 40. So I'll have 60 left. If you do minus 40, that will be plus 20 and plus 20. You're going to have that. Okay, now you're going to just do the math. Product over reactant, 20 times 20 divided by 60 squared. Okay, 20, that's going to be 400 divided by 66, 3600. Okay, so 4 divided by 36. Let's say 4 over 40, about 0.1, right? But it's gonna be a little bit more than 0.1. Okay, so that's the only thing that is bigger than 0.1. Okay, what I did was I approximate that. Obviously, 1 over 10, that's basically 0.1, but I know it has to be bigger than 0.1 because I round the bottom more than what it's supposed to be. Okay. All right, 22 is done. All right, let's see. I'm gonna peek at it because, yeah. Okay. Now let's see 23. What we're gonna do? Okay. Some of this is gonna be there. All right. KP is this. KP is okay. This is placed at allow equilibrium. Okay, some left. All right. How is it happening? So NH4, HS, and H3, H2S. Oh, about the same amount. Basically. Okay, so what we're gonna do is, where's my initials? Oh, easy. Doesn't really matter because doesn't matter what the initial amount is, right? Equilibrium pressure, Kp is gonna equal to P NH3 times P H2S because only gas for that part. Okay, so these two pressure is the same, x and x squared basically. So we can just say x squared. So this is equal to 0 0.070. 0 0.070 square root is equal to x. You gotta square root this basically. So I can actually rewrite this into 7 times 10 to the negative 2 square root. We're back to what we did before. That's why I said this is pretty much the same thing. 7, I can say this as square root of 4 or the square root of 9 basically. So then it is in between 2 or 3, okay, times 10 to the negative 1. So 0.2 and 0.3 right there. Okay. Alrighty, let's skip over 25. Kp for the conversion of, okay, a vessel is charged with this initial pressure at equilibrium. Okay, again, asking for partial pressures. Okay, this question's much more nicer. Notice that, see, I would tell you like that instead of KEQ. Let's say KP, KC, whatever it is. It's easier to say. Okay, and they also give you in ATM. So we're good. All right, so still ice. 0.123, that's the PCl5, PCl3, and then Cl2. Oh, backward to what we do before. That's 0, minus x, plus x, plus x. So then, at change, 0.123 minus x, x, x. Okay, what this is supposed to be doing. Okay. Oh, this is a KP. Yes. So we're gonna do KP equation. We're gonna do up here. 0.0121 equal to product over reactant x times x squared over 0.123 minus x. That sends over. You're gonna have your quadratic again. Kind of. No. In this case, yeah, we're kind of having again 0.0121 times 0.123. That will give you 0.0015 minus 0.0121 equal to x squared. X. Send it over. Good. Now you gotta do the equation again. B squared minus 4ac. So, yep. And then you're gonna solve for the x. So b squared negative b plus or minus square root of b squared minus 4ac over 2a. Uh, 0.0121 square minus 4 times 1 times negative 0.0015 over 2a. Okay, so I solve this. We're gonna pick plus again. Okay, so 0.0121 square plus. So that will give you. Oh, sorry, you can't see any of that. Right, that will give you. Okay, square root that one. And then so negative 0.0121 plus 0.078 divided by 2. Okay, so that's going to be 0.033. Okay. So 0.032 is x, and we're looking for PCl3, which is x, so 0.030 is this. Okay. Kp and Kc. You gotta convert it. Oh, you gotta use the Kp Kc formula to find it. Okay. So we're gonna get that. What's happened? So 1 Kp and Kc are the same. 1 delta n is equal to 0. So anything to the power 0, that's gonna make this whole thing 1. So when both sides has the same amount of gas, then it's gonna be it. Okay, so the first one. Alright, got it? Okay. 30. Given the following equation, okay, find Kp Kc, you're gonna have to do this. Kp equal to Kc RT delta n. So you're gonna say Kc is equal to Kp over RT delta n. And then once you solve this, you're gonna get your answer. Okay? Okay, so what we're gonna do, plug it in. Alright, let's do that. 1.06 divided by 0.082. You can say 0.6. I don't remember my paper. It's either say 0.21 or 0.8205, something bigger than 5. But yeah, something like that. It's fine. Okay. Oops, sorry, not that yet. Time, temperature. Okay, can't say in Celsius, so add 2783. And then the whole thing is gonna be over the power of how much a different product minus reactant. Product is 2, reactants 1, that means 1. 2 minus 1 is 1. So we're gonna solve this. So let's see, 0.08206 times 250 plus 273, 1.06 divided by the answer. Okay, so you're gonna get 0.024698, whatever it is. So 246, yeah. So if you move decimal to decimal, right there, B. Okay, 31. Le Chatelier principles. Equilibrium constants for reaction. Br2Cl2, 2BrCl. Okay, Kp, a closed vessel as 400 Kelvin, it charged it with 1 atm of, okay, and this, use a Q to determine which of the statement is true. Okay, basically they tell you what it is, so we're just gonna use this to find Q, and then we're gonna compare that with P, Kp. All right, product over reactant, this 2 squared divided by 1 times 1, because they're both 1. Okay, so that's gonna be 4. 4 is less than K. Basically Q is less than K, or you can say K is greater than Q. Guess what? It's gonna shift that way. It's gonna go that way until it's become equilibrium. Okay, so that's what it's saying. So okay, E is ridiculous because reaction. Okay, so essentially, if the reaction will go to completion, the reason wouldn't be that. The reason will be because your K is really large. Okay, reaction will go to completion if K is really large, very large. Okay. The equilibrium partial pressure for BrCl will be greater than 2. Okay, because it's gonna shift in that way for the equilibrium to get there, the D is gonna be correct answer because you will have more BrCl at the equilibrium. Okay, because my K is still bigger than my Q. Okay, that means A, B, and C are false, but let me just go through that. Equilibrium partial pressure, okay, not gonna be the same as initial value because it's not Q is equal to K. If Q is equal to K, A will be correct. Okay. B, equilibrium partial pressure Br2. Okay, Br2 wouldn't be greater. If Br2 will be greater at equilibrium, you will have the other way around sign. Q will be greater than K. Okay. Equilibrium total pressures will be less than that of initial total pressure. May not be true because you have 2 mole to 2 mole. In fact, it's probably more because you're making this side favor rather than this side favor, but approximately, yeah, it could be about the same. Okay. 32. You should already know how to do shift. Okay, 33, same idea. I didn't have a question on that one. Oh, wait, not that way, this way. I'm confused. Alrighty. A couple more. Okay, 37 and 38 and then 40. Okay, 37, Le Chatelier principle. Okay, we'll predict again. Increasing temperature. Same idea. This is exo. That means heat is product. If you're increasing this, that the same thing as you're adding product. If you add product, it's gonna shift toward reactant. Okay, it will shift away. Okay, so it's gonna shift this way. So that means partial pressure of these two would decrease and this one would increase. Okay, Okay, no, no, no. Okay, so that means either C or D. Now let's think. Because you shift this way, when you do product over reactant, what's gonna happen? Product is gonna go down, reactant is gonna go up. So therefore, equilibrium number will be smaller. All right, let's show you again. Temperature, increase in temperature, what's gonna happen? All right, same thing, because this is the exothermic reaction. Okay, same stuff as above. Less reactant, less product, more reactant. Okay, decrease in partial pressure of that. That is correct. Okay. All right, let's go through this. 39 and 40. 39, I just missing the arrows. This should be the arrow here instead of another plus. 40 here is, let's see. Okay, again, pressure, no change. Pressure, no change, that means equal mole on both sides. Nope. 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 Yes. Okay, equal mole. Okay, I think I kind of explained this one in class, but let me just go over this again. What is this happening to this graph? Okay, this just saying I go up. That means when you add I2, right? So that concentration go up, and then here concentration start decreasing, and then at some point stop and it's reach equilibrium. Okay, that's all it's saying. Okay, probably not as sharp as this for the equilibrium. Okay, so it's not that, it's kind of more gradual. It's changing back to the equilibrium. These two, I'm not quite sure how we're gonna say, because we don't really spike it. You're gonna have a spike or which one you add. So B probably not it. In a D, what happened? You are adding the Cl2. So again, it spiked it, and then the I2 move accordingly. Okay, because it's decreased, I2 is increasing or whatever. Okay, so let's see what is it saying. Graph above represents concentration versus reaction progress. Identifying the graph best represent following stress and shift. Okay, stress is adding I2. That would be an A. You added I2. I2 will decrease, and then ICL will increase over time, and at some point they equal out. Okay, 56. Removing Cl2. Okay, that will be a D. Okay, because it is removed it, and then after that it take a while to slowly come. Okay, all right, increasing the temperature. Okay, what's gonna happen if you increase the temperature? Both sides of the reaction will increase. But that being said, it will favor one side more than the other, because this is the exothermic or endothermic. If it doesn't say exothermic or endothermic, you can say the both sides kind of increase, because heat always make things kind of go a little faster. All right, so because it's the exothermic, so that means it's like adding this, so it's want to remove this, so therefore it's gonna favor this side. I2 will go up, Cl2 will go down. Go up, and then this will go down. That's what we're looking for, and then that's probably best fit would be. Okay, 48 said increasing the volume. What's gonna happen if volume increases? If the room getting bigger, it's gonna favor the side with less room. Okay, so increasing the volume, yeah, that would be D. Okay, so let's go to this one, 49 and 50, and I believe that's the end of this. Yeah, don't worry about this stuff, the solubility. I'll go over that in class, and we'll talk about it a little bit more. Okay. What happened here? N2O4 is decreasing, or NO2 is increasing. Okay, what's happening? at the time heat is applied to the system. Okay, heat is applied. So who is increasing? If heat is applying, it is favoring this side. So that means heat must be on this side. Okay, because heat is, if you add heat, it's gonna want to release heat, remove heat. So it's gonna go to the side without the heat. So it's gonna go to this side. So therefore, this is the endothermic reaction, and then so that will get these out. Now, what's gonna happen effect on KEQ? Well, let's take a look. You're gonna increase this, so increasing product and decreasing reactant. Product over reactant. Products increasing, reactants decreasing. What's gonna happen? It's gonna get bigger. Okay, lesson 1. Stress was applied at the time t in a data plot. Okay, stress imposed at the time is the results of. Okay, so what kind of stress happened here so that here H is getting decreased? A couple of things. If you add, but then it doesn't look like it's add because it just kind of go down. Okay, so let's see, maybe other thing is changing. So what happened? If you removed it, this one will go up. Now, if you put it in, this one will go down. If you put it in, this one will also go down. Okay, so adding these, well, not these chemical, but adding this, right? Well, I do not adding this. Adding this will make this go down. Okay, so adding this. Okay, so decreasing temperature, not it. You have to wait. Yeah, you have to increase it. Okay, so not that. Okay, adding of this. Yes, that would be, see, that would be CH3COO part. So that would be it. Volume had no effect, no gas. Okay, adding of HCl. If you add HCl, it's the same thing adding at H, but like I said, it doesn't quite look like it because if you add H plus, it's gonna spike it. It doesn't spike it on this one. So it is C. All right. I believe that's all for the thing. Okay, like I said, this one I'll go over that later. Okay.